All right, in this video, I'm going to be talking about the basics of remote sensing. We're not going to get too advanced in this video, but I do want you to know a little bit of the background of this technology and how it works, because that's really important in order to understand how we actually do this kind of work. So remote sensing is it basically means just collecting data at a distance. Okay, so classically, the most conventional understanding of this is taking satellites, and satellites take pictures of the Earth's surface. Nowadays, we have some other, other techniques like unmanned aerial vehicles or drones, but also for a long time, we've had aerial photography. So these are examples of remote sensing. And I'm sure that you've probably gone on Google Maps or Google Earth and you've zoomed in and you've seen, where your house is, or you've just looked at different places through Google Earth. And, that's an example of those satellite images that we can use to just gain a really good understanding of the context of where we live and what's going on, and looking for spatial patterns and all kinds of stuff, right? So there are a lot of uses for this, for these kinds of tools. Or what I'm going to do right now is just tell you a little bit about getting more advanced, beyond Google Earth, in case you have no or very little experience with this. All right, so the first thing to understand about remote sensing is that it typically uses raster data. So if you should have a little bit of basic understanding of GIS. And so we know that in GIS, we have our data can become in two different formats or two different models. One is vector, and that's points, lines, polygons. And then we have raster, and that's like the image. So, that's just like taking a picture of something, and the data is recorded in individual pixels, and it comes in a square or a rectangle, for example. And so each one of those pixels has one piece of data. And so in remote sensing, each pixel gets a value, and it's a number. So that number is called a digital number, or a DN. All right, and when we're talking about remote sensing or satellite remote sensing, we are usually talking about that DN, or the number that's in each pixel, refers to the reflectance of something off of the Earth's surface. So the camera's up there on the satellite, it points down at the Earth, and it takes a picture. All right, so pictures, when we take a photograph, it's not actually, painting the color, right? Painting the color of something in that pixel. Even on your phone's camera, it's not just coloring in a pixel with certain colors. It's actually recording a digital number, just a number. And so that number is going to refer to a certain amount of reflectance of a certain wavelength. So how that works in remote sensing is that our satellite remote sensing are usually equipped to take images, multiple images of different wavelengths. All right, so what does that mean? Well, let's talk about the electromagnetic spectrum just for a second, because this is really the heart or the core of remote sensing. So electromagnetic spectrum, we've got the sun, right? The sun is shining visible sunlight, but it's also shining all kinds of other waves, other kind of energy waves out that we don't see with our naked eyes. All right, and some of these you probably have heard before, like infrared, radar, gamma rays, right? All these kinds of things, right? Some of these other wavelengths that we can't actually see. So in remote sensing, when we have a picture of something, like if you look on Google Earth, you're really just looking at three wavelengths, okay? The red, the green, and the blue. And then you combine those red, green, and blues together, and that's what looks like a picture, right? That's a normal picture. It's actually a combination of three separate images into one. So you're combining red, green, and blue. So in remote sensing, each one of those separate images, like the red is separate, the green is a separate layer or a separate file, the blue is completely separate. If you looked at them individually, they would look kind of weird. And that's because it's just how much blue wavelength or how much blue light is being reflected off of the surface of that, whatever the picture is being taken of. And if we combine those together, that creates a composite image that looks like a normal picture, right? That's what our eyes would normally see. So in the electromagnetic spectrum, we've got our visible light, right, which is, the colors of the rainbow, but we also have some other wavelengths that we don't see. And for our purposes, the most important one is going to be the infrared the infrared part of the spectrum. And across the infrared, there's different types of infrared, and we're going to be working with near infrared. And so this is the part of the spectrum that's just past red, right? The visible color red. If you keep going past that, then you get into infrared, which we can't see. And then so the near infrared is just that first part of the infrared spectrum. Why do we use this, right? Why is this such an important thing for our project and for a lot of work? Well, if you're looking at things like vegetation, if you wanted to find out how healthy is a forest or a field of crops, you know, you could look at it with your eyes and you could say, oh, it looks green, it looks okay. If there's a huge drought and all the plants die, you see the plants turn brown, right? So that's the visible light being reflected. That's a combination of red, green, and blues that reflect, and we can see that. But what's really cool is that plants and the way that photosynthesis works within the leaf structure, it reflects certain parts of the wavelengths of electromagnetic spectrum in different ways. So when we look at a leaf of a plant and we see that green, that's because a lot of the red sunlight is being absorbed. The red is not being reflected back to us, it's being absorbed. Now, if we compare that with the near infrared part of the spectrum, then actually because of the leaf structure and because a healthy leaf that is doing photosynthesis and producing and doing all of that good stuff that a healthy plant is supposed to be doing, it actually reflects a lot of near infrared wavelength. And so we can use our remote sensing tools and we can look at a near infrared image, and we can compare that to a red image, and we can get an idea of how healthy is that vegetation. Because look, if the plants die and turn brown, it's already too late. You know, it's much too late. All right, so that's kind of a quick and dirty version of using remote sensing to analyze vegetation change. So the tool, the technique that I just described has a name and has an initials called NDVI, and that means Normalized Difference Vegetation Index. So this is a way that we can use satellites to look at large areas and understand broad changes in the environment. So for this project, we can also look at disaster impacts. So if a hurricane passes through, or if a volcano dumps a lot of ash onto an area, you know, if we try to look at it with just the visual, with just the visible light, it can be sometimes hard to tell how much damage there was, because, you know, maybe the leaves are on the ground and they're still green, for example. And also, when we're just looking at very large areas, you know, it's hard to tell, are there broad patterns just by looking at the visible, a visual picture of it. So we can use our tools like using near infrared and the red band to really get a much better evaluation of impacts and of vegetation change. So we've got an idea of what we use remote sensing for. You know that this has to do with the electromagnetic spectrum, and we use different parts of the spectrum to do our work. And so how do we store our data? So one thing to know that when we're dealing with remote sensing data is that there's different wavelengths like near infrared, red, green, blue. They're stored in different files. It's like different pictures, right? But the technical language we use for that would be called a band. So we're going to be using some images from a satellite called the Sentinel-2 satellite for this project. And Sentinel-2, it stores the blue light. A picture of blue reflectance is in band 2, for example. Band 3 is green, band 4 is red, and band 8 is the near infrared. So just those numbers, you'll see those again later on, but that's just an example of how our data is stored. All right, going back to how we talk about raster and vector. And so if we're dealing with raster, with images, we have to also understand resolution. So each cell or each pixel in an image has a resolution, and that means it's a square, right? If you zoomed in on a satellite image or any photograph, right? If you zoom in close enough, you'll end up seeing little squares, and each square only has one color in it. And so for remote sensing, that square it's an area, right? So each side of that square covers a certain amount of the Earth's surface. So some of these satellites that we use to analyze very large areas, like an entire continent, that might have a resolution of, say, 250 meters. So each pixel covers 250 meters by 250 meters, right? Each side of the pixel is 250 meters by 250 meters. If we're trying to study a much smaller area, we need to have a different kind of resolution. So if we're looking at small islands in the Pacific Ocean, a 250 meter by 250 meter pixel, that kind of resolution is not going to give us anything that's really useful on the scale of livelihoods, right? So of how is customary land being affected by disasters, for example. So we need to have a different kind of resolution. So the Sentinel-2 satellite provides us with data at a pretty high resolution, and we can get it as small as 10 meters. So that means it's 10 meters by 10 meters if you look at each pixel. That's how much ground it's covering. All right, resolution is very important in remote sensing, not just because of your study area, right? So what I just told you was, the resolution, we have to pick the right one for our study area, but it also affects your storage of your actual data. So an image where the resolution is 250 meters, that's going to be a much smaller file size than something with a really high resolution. And you probably know this, you probably might play around on your phone, and if you set it at like a really high quality photo, you don't have as much room on your phone's memory, for example. And if you set it at a very poor quality photograph, you can take a lot of pictures. And so that's because each cell or each pixel is a piece of information. That's like one small piece of data. So the higher resolution it is, that means that there's more information that has to be recorded in each file. So you've got to keep this in mind, because that's just part of we're doing remote sensing work. All right, so what do we do? Like, what is some background of what we do in remote sensing? And this is not a true remote sensing course that we're in right now, but if you wanted to get into the remote sensing field more in a bigger way, here's the kind of things that you should do is, you've got to understand how data is acquired. So we have to understand the satellites. We have to understand the resolution of the pixels. Right, and there's also something called spectral resolution. And spectral resolution tells you how many wavelengths, or how precise the picture is in terms of wavelengths. So how many bands of data can it get? Does it just get one infrared wavelength, or can it get near infrared, mid, and far infrared? Things like that. All right, some other things that is useful to know, but we don't have to work with that in this project right now, is you usually have to do quite a bit of pre-processing with your images. So we've got to make sure that all the satellite images are ready to work. We've got to make sure that they have a coordinate system. So we have to make sure that they are registered to a geographic coordinate system. Otherwise, it's just a picture, right, that you can't actually put into a map. And we also sometimes have to do geometric correction, so controlling for the curvature of the Earth's surface and that sort of thing. Other things that we have to do in remote sensing is called atmospheric correction. So that if you're dealing with satellites way up in space, taking a picture of the ground, the photograph has to pass through a lot of atmosphere. And of course, there's just stuff in the atmosphere. There's aerosols, there's, things that we can't see, pollution, there's just particles in the air that can make distortions happen. And so some of our image providers will do that correction for us. So in this project, we're going to be using images that have already gone through all of those corrections, and they're ready to use. One thing, though, that can never be corrected if we're just taking a picture of the Earth's surface is clouds. So clouds, if we're doing vegetation analysis and we need to get an actual picture of the plants, whether that's a visible picture or with near infrared, we actually have to see the ground. And so clouds are the biggest challenge when we do this kind of work, because clouds block the view. And it's not just the clouds themselves, but often there are shadows of the clouds that are in another location, right? So the cloud will be here, but then the shadow, might be in another place. So that can cause a lot of problems. So when we look for images, we often are limited in the dates that we can use for collecting images, because there just might be cloud cover on certain days. So if we're working if we're doing research on a place that has a lot of clouds, say a tropical environment near the equator where there's just a lot of clouds all the time, it can be pretty tough to get the right data, the best times. So for example, if we're trying to find impacts of a disaster, and we would want to collect and find images from before and after the disaster to see what it was like before the impact and what it was like after the impact, we have to go through and spend a lot of time finding images where there is very little cloud cover. So for the project that we're working on right now, or for an example project, let's say you wanted to analyze the impacts of a hurricane in a tropical environment. Well, hurricanes, of course, is a giant cloud, and we've got to wait for that whole storm system to move out, and before we can find images where there's a cloud-free day. And so you've got to really search through the available data to find the ones that are going to work best in your project. Okay, so let's look at an example of how resolution makes a difference. So I'm sure that you've all looked around in Google Earth before, and in Google Earth you can zoom in and out and in and out, and that image will constantly update, and it will always look really good based on how far in you're zoomed in or out. And that's a little bit misleading as to how satellite images work. And the reason is that each one of those views, each zoom level, is actually an entirely separate picture. And so I want to just show you a little bit, like we're going to compare two different resolutions here. So what you see here on the screen are two satellite images. This is of the southeastern part of Espiritu Santo Island in the South Pacific country of Vanuatu. We've got a few other islands nearby. But right here in along the coast of this island is a small town called Luganville. And the image on the left here, that's 60 meters resolution. And the image on the right is 10 meters resolution. And when we're zoomed out this far, they both pretty much look the same. But we have to keep in mind that the image on the left, 60 meters resolution, means that each pixel that makes up this image covers a 60 meters by 60 meters area of the ground. So if we zoom in as far as we can see that we can start to make out some details, but it's a little bit vague. And when we zoom in quite a bit, we can actually see the individual pixels that make up the image. So this is what you never see on Google Earth, because if you zoomed in like this on Google Earth, they're actually dynamically loading new images at different resolutions. So this is actually the main part of the town, and we can't see it at this resolution. All right, if we go over here to the 10 meter resolution image of the same thing, and we start zooming in, we can actually make out much more details here. We can see streets, we can see some of the houses, we can see some green spaces. All right, it's still not maybe as detailed as you would want if you were doing highly detailed studies of houses, for example. For that sort of thing, you'd need an even greater resolution, like 1 meter or something like that. But for understanding vegetation change at a local level, 10 meters resolution is still a great thing that we can use. The other side, right, the flip side of this is that with a lower resolution or a coarse resolution, the file sizes are much smaller. And so that 60 meter resolution image, that file is 3.8 megabytes. Compared to the 10 meter resolution picture, that whole thing, the whole image, is 135 megabytes. And here you have a 10 meter image from Sentinel-2 of the island of Ambai in Vanuatu. And this image was taken on February 13th, 2020. So this is just a few weeks before the hurricane hit the island. So another thing I should tell you is when we have remote sensing, our file names that we get from the data source, just like a lot of our GIS data, can sometimes be a little bit complicated to understand. So this is our file name is T58LGH. That has to do with the region. And so that's just sort of a naming convention by the people who run Sentinel-2, is that this image that's part of the world. They've just called T58LGH. All right, and then we've got underscore and then 2020-0213. That's the year, the month, and the date. All right, and then we've got some other numbers here. And then we've got an initial TCI. And so the TCI means true color image. So this is that composite that I was talking about, where this is actually a combination of 3 different bands. This image is actually a combination of 3 different images, and they've been put together to create a true color image. And we see that it's 10 meters. So this is some of our study area that we'll be working with. And we see that we've got in the middle of the island is a volcano. That is also another source of risk. There's been some volcanic eruption the past couple of years that have caused some evacuations and a lot of environmental damage. And so just as people were recovering from that, a hurricane came through. So that's what we're actually looking at here. Most of the people live on the coastal areas, and we can see from our true color image, we can see some evidence of settlements, some villages, and this is a runway right here, a grass airfield for the airport.